Everybody, in this video we're going to be discussing the concept or the idea of slope, okay, and hopefully answer two major questions. But first of all, what is slope, okay, and how can we find the slope of, say, a line? And you have to know that, of course, if you're in calculus, a lot of the time the idea is to find the slope of a curve at some individual point, which is hopefully what we all work towards. That's what I hope. But it's easy to start basic with this idea of a line and finding the steepness or the slope of a line. And it's interesting that I already say steepness because first question, what is slope? If we think about this word slope, that's really what we're discussing is the grade or the steepness of something that is either rising or falling, or maybe is not rising or falling at all, or has no slope. But it's an interesting concept because the fact of the matter is this: we assign a number to it or an index, to it. But the way we measure it is kind of talking about, imagine if you were walking up some stairs. You said, man, these stairs were really steep, okay? And they look something like this, all right? The fact of the matter is, if we were to judge the steepness of this set of stairs right here, we would have to take into account both, not just how far up it would go on each, say, iteration or each step, but also how far it would go over. So if we kind of judged a set of stairs as being steep, you would probably assume that, wow, these are going up way more than they're going over because they're really steep. Or if we had a set of flat steps, you would say, okay, compared to how far it's going up, it's going way out, okay? So the fact of the matter is, we talk about two kind of ideas here, but rise of something compared to its run. We have to compare these two quantities, and their comparison or their ratio necessarily articulates how steep something is. Okay, so you're going to notice right off the bat here that I've drawn in a couple of points over here, but we say in general some points x1, y1, and point x2, y2. But again, if we wanted to judge the steepness of this, especially in the rectangular coordinate plane, because of the fact that we can find the directed distances back to the x and y axis respectively of each of these points. But the fact of the matter is, we would want to compare this run here, okay? And maybe I need to switch colors here. This run to its rise. And of course this line here, you're going to notice already that it runs more than it rises. So I would say this is naturally kind of a flatter slope. But of course we want a number for this, okay? So the first two things we want to find are how far did it rise and how far did it run, okay? So again, the nice thing about the rectangular coordinate plane is, we'll start with rise here. We know that this top y value from this top point here is the y value of the second point, and the bottom y value is this y value of the second, or the first point, excuse me. But the fact of the matter is this: if we wanted to find this distance right here, we would define that as the difference between the y values. So the difference, of course, would be y2 minus y1, or y1 minus y2, but we'd say, okay, the absolute value of that. We just want the magnitude. Okay, and then another notation you might see here is we use this delta to represent difference, but the difference in the y values. Okay, whereas now we talk about this horizontal distance here, that would be the difference in these two x values. Okay, so we say if this is the x value of the second point right here, and this is the x value of the first point, we'd say this total distance from the first one to the second one would be the difference between the two. So naturally, just kind of like when we talked about the distance formula, we'd say that this distance right here is the difference between these two, and we could also call this delta x, or the difference in the x's, okay? So to compare these two, what we're going to do is we're going to set up a ratio, but really important letter I'm going to drop on here, the letter m. Now, I've read several different things. One time I read, I think, that m came from a French word for slope, and then I've read several other things that say m just because m. There's no maybe reason behind the rhyme why we use m for slope, but we do, and we use lowercase m. I do want to be clear on that, lowercase m. But what we're going to do is we're going to call slope the comparison of how far something rises to how far it runs. And again, it goes back up to this idea of if something's steep, it's going to rise much more than it runs, or if something's flat, it's going to run much more than it rises. But this comparison, this ratio, and what we would like is a number, really. So what we'll do is we'll assign one, but we're going to derive this formula first, okay? So knowing that the rise of this, given 2 points, x1, y1, okay, and x2, y2, we could define the rise, like we said, as delta y change in the y values over or compared to the change in the x values. Just a comparison here, okay? But we've kind of defined these as being differences. So we'll say this is the difference in the two y values of the 2 points, and this is the difference of the two x values of the 2 points, okay? So this formula, again, I'll write m. You know, this is all reflexive, transitive, all those fun properties, but this is one you want to write down and keep in your pocket, okay? This is the slope formula, the slope of a line through 2 points, okay? So this is something we're going to be using often to determine the slope of, say, a line through 2 points, which is what our ambition here is in this case. So just real quick, let's try this guy out, and then we're going to move on to finding the equation of a line using point slope. The equation of a line using point slope form, okay? But say we wanted to find the slope of a line passing through the points 3, 4, and 5, 7, okay? So first what I'd like to do is illustrate this. You know, people get into upper level math and they tend not to illustrate things. Or they do if they're good students, okay? But since I've drawn this in, I do want to label it. That's a good habit. 3, 4. And then we say 5, 7. So over 5, up 7, be about right here. Already we can draw a conclusion about this. You notice if I draw a line through this, it's heading uphill. So the important thing to know is this. If it is increasing, our line here from left to right, we say slope is positive, and we should get a positive ratio when we do this, okay? But the first thing I want to say is this. You know, this is a convenient set of points. I can't promise you, especially if you're in my classes, we're going to be using points this simplistic, this trivial. But the fact of the matter is this. If it went from an x value of 3 to an x value of 5, of course, this naturally increased by 2 steps to the right. It ran 2. And from an x value of, or a y value of 4 to a y value of 7, this increased by a magnitude of 3, or not a magnitude of 3, but by 3 steps, okay? So you're noticing already that this is rising much more than it runs. Not much more. I'm out of control today, I guess, but rising more than it runs, this would be necessarily maybe classified as kind of a steep-ish line. And we could say the slope already, we say m. m is equal to rise of 3 over run of 2. What I'm telling you is this. If the points are this convenient, use your fingers and toes, please and thank you, okay? Fingers and toes, that's what we'll do. But the whole point of this was to kind of see this formula in action and use it. So we say slope, okay? You know, I always kind of recommend when you evaluate for things that you put in blanks. And this is just kind of me. It's a good habit. Keeps you from messing up on negatives. It happens. It's like running the hurdles. Sometimes you get caught. But we say, okay. So y2 minus y1. The y value of the second point, of course, here is 7. Y value of the first point was 4. On the bottom, the x value of the second point was 5. X value of the first point was 3. So now evaluating this, we get 7 minus 4 is 3. On the bottom here, 5 minus 3 is 2. And there's our 3 halves, okay? And we just simply say that our slope is 3 halves. Don't let anybody tell you can't write this as a slope of 1.5, okay? But I will tell you this, it is much more convenient to leave this in a ratio format because you can see a rise to run ratio and maybe help you define the slope of a line. Okay, now real quick note. In the next video, we're going to be talking about the point slope form of a line, okay? So I want to kind of take your eyes and have you follow back down here, and just real quick, because I think this video is getting kind of long. But let's kind of look at this formula here. We could consider y2 minus y1, since it's a parenthetical quantity, as some number, okay? Some number delta y, for example, okay? And then on the bottom here, since this is in parentheses, these are in parentheses, it is also a number. But what would happen, my question is, if we took both sides of this equation times this number, x2 minus x1, or times delta x. So for the sake of shorthand, we say m is delta y over delta x. But what I'm positing is this. What if we were to take both sides times this number, delta x? First things first, those two quantities should cancel, and what we're left with is delta y is equal to delta x, this number, times m, or our slope. Another way to look at this, though, is y2 minus y1, which was delta y. That has to be equal to m times x2 minus x1. Okay, this is what we're going to be exploring in the next video, so keep this in mind.